get started here. We begin with the word of prayer. So get up here. Heavenly Father, we thank you for this day. Again, I thank you for this class and this time we have to meet and study your creation. Just pray that you would bless our work today, Lord. In your name I pray, Lord Jesus. Amen. Let's see here. So I need to talk to you guys about visualizations, existence and uniqueness, and then, so technically speaking, I'm skipping past applications, talking about some issues about well, it's really a first application in some sense that we're going to look at in here is differential equations as it applies to geometry, all right? So particularly the geometry of curves, and so I think as a starting point, it's helpful for us to just take a step back and look at how does the calculus of curves in the plane work, all right? So this is my section 2.6, which is on page 47. Visualizations. Well, I'll just say section 2.6. So I'm going to begin by looking at, if we're talking about a curve in the plane, we kind of have two options, right? The one option is to look at an equation like f of x comma y equals to k, right? The solution set to an equation is a level curve. So this is as a level curve. Or you might call it the graph of an equation, right? Something like that. And then the other way, which is seemingly quite different, is r of t equal to, let's say, x of t, y of t. So this is we usually call it a parametrized curve. So just, so I don't lose you guys, just to make sure we understand each other what I'm talking about. A good example of a level curve I always come back to is just a circle. So you could have the circle x squared plus y squared equals to, say, r squared, right? Here I'm choosing k equal to r squared. My big F is x squared plus y squared, right? That's a level curve. To parameterize that, one way you could do it would be to look at, say, r cosine t, r sine t. So this is, but here, of course, I have to say for what? For 0 less than or equal to t less than or equal to 2 pi. Right? So we could parameterize the circle. Now, is the parameterization of the circle unique? I mean, by no means, right? There's infinitely many different choices for how to parameterize the circle, because this one goes around it at one particular speed, right? But if I was to take this t here and change it to 13 times t, it'd still parameterize the circle, but it would go 13 times as fast, right? Or I could replace t by minus t, and then it would wrap around the circle. Instead of the counterclockwise way, it would wrap around the circle in the clockwise way, right? So parameterization of a curve. So the circle, you can kind of picture like this. It's just the set of points that is radius r, right? Is this clockwise oriented or counterclockwise oriented? The answer is no. It's a circle, right? But over here, if we're talking about the circle, well, it has an orientation, right? This path, specifically, this is r of the set 0 to 2 pi. So it's the output. It's the image under the parameterization of that interval. In contrast, this circle is actually the inverse image of the set just containing, well, in this case, r squared. Right? It's the set of all points that maps to r squared. So it's a fundamental difference in description. Do we describe something as a solution set to an equation, or do we describe it parametrically, right? We have these two different ways of doing things, and we do both. Now, if we're describing the same curve in both ways, how do they have to be connected? If you have a parameterization of a level curve, what does that mean? If r parameterizes f of x comma y equals to, say c, whatever, k, then what does that mean? We must have f of r of t is equal to k for all t in the domain of the parameterization. In other words, if you have a legit parameterization for a level curve, when you plug it in, it has to work, right? So for my pet example in the blue, that's pretty easy to check, right? When we look at f of r of t for my example, that looks like f of r cos t, r sine t, which is equal to r cos t squared plus r sine t squared if we follow the instructions for the f map here, which of course is r squared cosine squared t plus sine squared t, also known as 1. So lo and behold, hooray, it works, right? It's a parameterization of the circle. So we can test whether or not we have a parameterization by plugging in the parameterization into the defining level curve if we're given a level curve. But of course, you don't have to have a level curve to describe a path. You can just as well describe it parametrically. These are two different competing viewpoints. So what's the deal with partial derivatives of the level curve? How do they relate to the tangent vector to the corresponding parameterization of the curve, right? So let me state that question again. How do the partial derivatives of the level function, partial f, partial x, partial f, partial y, relate to dx dt and dy dt for our parameterization xy? I think this one's done. So what do you guys think? Does anybody know? Can you tell me? Do you remember Calculus 3? You're like, we didn't learn this in Calculus 3. We just do problems from the book. We don't have any conceptual understanding of anything. Because who cares about concepts? We just want to solve problems. No, you didn't say that. I just said that. Let me retract my... Sorry, I'm recovering from teaching physics for Dr. Scambordis. Those students, they're dead. You guys aren't those, are they? Anybody here from that class?
He said they're dead.
Oh, sorry, the rest of your class, they're horrible. You're great. You're great, but no, it's just dead in there. Like, it's dead. What did he do to you guys? Was there some kind of... Well, anyway, I'll behave. So how about this? If we differentiate f of r of t, how does that work? Let me write it again. This is d dt of f of x of t, y of t, right? This is a composite. When we take a derivative of a composite, we must use the chain rule, right? And the chain rule here, the multivariate chain rule, looks like the following. Partial f, partial x times dx dt, plus partial f, partial y, dy dt, right? Now all of that is equal to the time derivative of the left-hand side, which was what? If this is what I'm setting up over here, this deal right here, right? I'm supposing we have r, which parameterizes a level curve. Continuing that discussion, I'm assuming that f of r of t is equal to k. K is a constant. What's the derivative of a constant? 0. Aha. So what this says then is that the vector partial f partial x comma partial f partial y, right, has to be perpendicular to the vector dx dt dy dt, right? This is the gradient of your level function, and if I was to do it properly, it's at r of t, because it has to be evaluated at the inside function. That is the velocity to the path, or if you like, dr dt. So this is the relation between a parameterization and its level function. All right, this is the way they're related. So that's one thing we should keep in mind. Now, let's see here. So let's try to apply that. Like, suppose you have an exact equation. Okay, so with all this in mind, consider m dx plus n dy is equal to 0, right? If that's the case, then what can we say about the solution to this as it relates to m and n? Okay, let me say it this way. If r of t equals, say, x of t, y of t, parametrizes the solution to star, then dr dt is perpendicular to what? What is the solution to the level equation? Remember what the solution is to an exact equation? I forgot to say, this is an exact equation. I said it in words, I didn't write it on the board, so I guess it doesn't count yet. Exact. Exact equation has solution what? F of x comma y equals to a constant, right? And what's the relation geometrically to that level function and to a parameterization of the solution to the differential equation? They're what? They're perpendicular, right? So then this has the gradient of f at the solution perpendicular to the parameterization, the velocity of the parameterization. Let's see here if I can say a little bit more here. I guess there's another idea I need to bring into play in order for us to understand this discussion entirely. Tell you what, I'm going to do an example before I bring in the next geometric idea. Let's see here. So I guess we can just continue with my blue example. Let's just kind of flesh that out here. That's probably the best thing to do. Okay, so we have f. Is there a question? Because I hear people whispering. If there's a question, it should be directed to me. There shouldn't be whispering during class, because I hear these whisperings, and then I start wondering if it's actually me hearing it, or if it's just in my head, and that's disconcerting. So f is x squared plus y squared. What's the gradient of f? We got 2x, 2y, right? Now, the parameterization that we discovered here in the blue was r of t is what? We had what? Cosine t, my bad, r cosine t, right? R sine t. So if we calculate the derivative of that, we get what? Minus r sine t, r cosine t, right? Trash. Hey, if I get to 20,000 subscribers, pizza party.
Wait, actually? Wait, deal?
Let's make it 25. I'm at like 19.7. You guys, someone here knows how to make bots, so I should at least give you a little bit of work. At least give me 25. 25. Okay, maybe 20,000. I gotta check with my wife. Sorry. Probably though.
You should like clip your lectures.
I clip my yeah, I know. I'm not playing the game correctly here. Nabla f of r of t.
When are we getting another basketball video?
I have to drive up engagement over break, you know. So that's the kind of. I may make a pool video soon. I don't know. You heard it here first. Yeah, maybe. So context here is it's the gradient vector evaluated at the same point we're thinking about the velocity vector Those are the things that are perpendicular. So we have to compare dr dt to the gradient of f at r of t. So the gradient of f r of t is what? It's 2x, but x is what? X is, oh, come on. That's the second time today. Hey, Min, I'm teaching. Okay, yeah, tell you later. I love Min. Min's great. I'll tell you a story about Min. Once I was writing a paper with Min, and my computer wasn't working, so I had to use his miserable Apple computer. And so I'm at his apartment. It's over winter break because the due date for this thing is like December 31st, right? So I'm trying to type up this math paper on the stuff we've been doing in the fall. Min and a couple of other students then. And Min is, and I'm at this shaky kitchen table, right, with this stupid Apple computer I hate. And what's Min doing? Is Min calmly sitting by me, helping me, figuring out like what code I'm missing and stuff like that, why it's not compiling, any kind of helpful constructive criticism? No, what's Min doing? Min, for some reason, has a hotel bell. I don't know why, but he has a hotel bell, the kind you ring for service, and he's sitting beside me, repeatedly dinging the bell like this. Ding, 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 ding. I don't know why, but that's what he did. And that's just kind of typical Min. He was also singing the Everything is Awesome song before I saw the Lego movie, which was kind of like, what are you singing? And he could do a really, really, really nice Gundam style. That's the time period we're talking about here. So you guys were what, toddlers? Let's see here. I don't remember how long ago this was. Pre-COVID for sure. Yeah. So what happens here? You got yourself a 0. All right. So the tangent vector to the parameterization has to be perpendicular to the gradient vector of the curve, the level curve, which forms the solution. This is the relation between these things. Right, yeah. So another thing that we can look at, definition, is if we're given a vector field. You guys remember vector fields? Yeah, yay, very good, all right. So let's say f vector.
Sir.
Oh, I'll get it in a second. Thank you. XY is, let's say, P. Fine. I hate writing, like, let's not write this XY dependence, but I mean, I've already written it, so it can't be unwritten. But, you know, like, generally speaking, I just say F is equal to P comma Q, but let us understand we're talking about functions of X and Y, all right? Man, the glare on this board, it's annoying. There's like this one strip where I can't write because it's like the sun, you know? Because there's like a missing vertical blind over there because it fell off or no longer turns or something. All right, so given this vector field, we say R, let's say a mapping from, you know, the domain of R, which is a subset of the reals, to R2, is an integral curve, aka streamline, of f if f of r of t is equal to dr dt. Now let me expose what that means more explicitly. So if we, you know, dr dt is what? So we're talking about p comma q equal to dx dt comma dy dt. I'm probably stupid window. I mean, I like the window. I feel more awake here, but it's also annoying. Should just spray paint part of this window. Oh, you know what I could do? I get the snow, like from Christmas time, and just like snow.
Okay, just turn the blinds. Like, do they go to the right?
Well, if they were, maybe. Good enough. So this is what we're up against, right? So what am I trying to solve? I'm trying to solve dx dt equals to p and dy dt equals to q. I need to solve these two differential equations in order to find the parameterization of the integral curve. All right? So let me actually do that for an example, and this will give us more practice with basic differential equation stuff too while we're at it. So suppose we have example what? I guess 2. This was all example 1, wasn't it? All the blue is example 1. I don't know. I guess you guys can figure it out. Example 2. If I have my vector f equal to, let us say, minus y comma x, that might be interesting. All right. In this case, I'm trying to solve dx dt equal to negative y and dy dt equal to x. Oops. I think we don't have the technology to solve this just yet. Sorry. So if you'll forgive me committing a slightly indecent act here in terms of the mathematics, because we haven't done this yet, but it's pretty easy to solve this. Like all you do is just like shove the first equation into the second, and that gives you like ddt of dy dt equal to minus y. If I plug the second equation into the first equation, which then gives us the equation like y prime prime plus y is equal to 0. I will then use a principle of solving differential equations known as guessing, and write down the solution is y is equal to r, I don't know, sine of t plus a phase angle phi, let's say. You can try it out. If you twice differentiate that function, what you get? Differentiate once, get cosine. Differentiate again, get minus sine. You get minus r sine of the same thing. So when you add it to itself, the second derivative to itself, you get 0. So you can easily check that this is a legitimate solution. Now we will discuss a technique on how to find that in about a week, maybe 2, week and a half. I don't know, somewhere there. If I know that, then what's x? Well, x is equal to dy dt, so we can figure that out. Yeah, that's just what? That's r cosine of t plus phi. And so there you go. Your integral curve is, what we got here? R cosine of t plus an angle, comma, r sine of t plus an angle. So this is, parametric, parametrized integral curve for f. Obviously, like generally speaking, finding these directly, it's a little bit troublesome, right? Because if the dx dt and the dy dt, if they both involve x and y, in order to solve them, we have to somehow to untangle x and y, so we get just a differential equation in x, or just a differential equation in y. We don't have any technology to do that just yet, except for sort of like algebraic chicanery, which we don't know quite enough of to be successful in this endeavor generally. But the good news is there's a trick. So what if instead of finding the parameterization for the integral curve, we want to find a level function, we want to find the integral curve presented as a level curve. How could we do that? How can we find the integral curve to f equals to p comma q as a level curve? The answer is kind of stupid. Check this out. So basically, you want to have, well, I'm not gonna derive it. I mean, we could derive it, but if you'll forgive me, I'm just going to show you. So what we want is we want to figure out how to figure out, to figure that out, essentially it begs the question, what should dy dx be for this level curve, right? If we could figure out what that is, we've got a prayer of finding a procedure to calculate this thing. So, well, dy dx, we should just do what? We should just do dy dt divided by dx dt, right? Surely I can divide the numerator and the denominator by dx dt. Hey. Now, if you want me to be less sketchy, we could go through a chain rule style argument to like derive what I'm doing from calculus. That could be done. But let me not do that in here because we should spend more time solving problems than that kind of thing. So, well, by assumption, this is what? dy dt was supposed to be what? Q, right? And this is supposed to be P. So the takeaway message here is, you just need to solve, if we solve dy dx equals to Q over P, this gives, streamlines to the vector field P comma Q. That's your takeaway thing to know how to solve problems. Because I ask you to find some integral curves, or if you like streamlines to vector fields, this is how you do it. I'm sorry, I seem to have hidden it behind some heads. Unfortunately, I'm ethically bound to not remove heads of students in the front row. Although, what if we could find some sort of like active camouflage hat that they wear that just bends the light around them?
I don't know.
So you have to wear like a not a tinfoil hat, but like a predator style hat. You just see through them. Oh, okay, so let's do that here. For my example, minus yx, what are we up against? Did I ever move the camera? I did. Okay. It's like, oops. It's a little late to ask, right? But let's finish this here, this example. So for f equal to, what was it, minus y comma x, we want to look at dy dx equals to, what did I say, q over p. But for us, that is x over minus y. Can we solve this, differential equation? So at the moment, we're going to find Cartesian. We're trying to find the Cartesian form of integral curve, all right? The level curve is the Cartesian form, right? It just has x and y, there's no t, right? Okay, great, so can you guys solve this? You're like, I wish my homework was this easy, right? No, there's some hard problems in the homework. Minus y dy is equal to x dx, like that, right? Separate, integrate. Actually, if I was smarter, I would just do this, x dx plus y dy equals to 0, which is, of course, the differential of 1/2 x squared plus y squared, 1/2 y squared equals to 0, which shows that it's an exact equation, and the solution is simply, x squared over 2 plus y squared over 2 equals to a constant, which I kind of would rather just write that as x squared plus y squared equals to r squared. All paths lead back to the circle today, don't they? These are very different problems that all take the circle as a solution, yeah? Do you see how these two solutions are related? It should be clear to you that the parametrized flow line we found over there, the parametrized integral curve, right? If I was to take that and plug it in here, it works, right? That is, in fact, a parametrization of the circle of radius r centered at the origin, right? What is lost in finding the Cartesian form of the integral curve? If you're a real purist, you might say it's not really a streamline because it's lost a sense of direction, right? The parameterized version, it does point things in the same direction that the vector field's going. That's lost in this procedure of dividing q over p, right? Because if you think about it, if I had minus q over minus p, it would give me the same ratio, right? So this is only good up to that consideration, but it is nevertheless, I think, an interesting problem. Yep.
How did you get equals c? Why is that not negative c?
Why is that not negative?
In my mind, that would be
What?
you would add c. I'm sorry, this would be in the second.
Oh, well, this is a theorem. If we have the total differential of a function of two variables equal to a constant, the solution to that is the level function equal to a constant.
Okay.
So you could also separate variables if you like, right? If you did that, that's also fine, you know. I think everybody can do that. So I thought I'd do something that would confuse you. Or maybe not you, but as many students as possible is my goal. So minus y squared over 2 equals x squared over 2. Sorry for this hideous Carolina blue. Equals to, that looks like an r squared over 2. Oh, excuse me, minus r squared over 2. And then that gives me x squared plus y squared equals to r squared. As you can see, I judiciously, what's the word? I conveniently chose my constant so that it would be the same equation, but, you know. But yeah, we could separate variables as well. So this is a new problem we have to solve. If you're given a vector field, you can try to find the integral curve to it, right? At the moment, I better only ask you to find the Cartesian equation for the integral curve, because if I ask you to find the parameterization for the integral curve, it might give you a system of differential equations that you don't yet know how to solve. We will learn how to solve these kinds of systems of differential equations a little bit later in the course. There is a method. We can solve pretty much all of them as long as these formulas aren't too ugly. If they're linear, we can solve it. There's a general method. The other thing to notice here is, let's see here.
Quick question.
Yeah.
Why is it minus r squared over 2 instead of like plus r squared over 2?
Oh, I wrote the constant that way so that the equation would look the same after I did the algebra.
Okay, gotcha. I gotcha.
I was raised by physicists. We do this. Like, I was a physics major, and all the time we'd integrate some equation, and like, it wouldn't just write plus c, he'd write like, plus the square root of c divided by 3, and you'd be like, what's that? And then 2 algebra steps later, the c would appear where you want it to be in the nice final formula. This is like that. It's just nonsense. So, yeah. But when you add a constant, you're free to, format the constant any which way you like. Although, it does beg certain questions. I can't have just any constant I want when I finally do the algebra here, right? If I want the solution here to be non-trivial, I do need to have this to be a non-negative constant, right? If it's 0, it just has the origin. If it's positive, you got a circle. If it's negative, you got nothing. So, nothing. All right, so I think that's a neat problem. I got a bunch of pictures I'm going to share with you guys. I guess at this point, actually, I should share the pictures because it probably helps complete the thought here. So let me do that. So did you guys remember? See, it kind of really depends on which calculus 1 you had, where you had it. when you took Calculus 1, at the very start of things, when you were doing derivatives, did you ever look at like pictures where you have like the slopes of all the different curves plotted, and then you like connected the line, like connected the slope? So you did that, but not everybody. These are called isocline plots. So like in some sense, the integral curve thing we just did, in some sense, is connected to that idea of isocline plot. The isoclines don't have a sense of direction. Direction field, on the other hand, well, they have a direction. Sorry, I got too many tabs open. I'm trying to find something. Oh, yeah. Oh, there it is. Woohoo! Make sure I've got my notes. All right. All right, so we are just in this section 2.6 here. And so this is the calculus I started class with, all right? Right there. Right here is a so-called isocline field for x dx plus y dy equal to 0. I think I need to, it's going to take me a minute here to explain why, how to understand this. See if I can think of it. So what we're looking at, I guess we're back to that differential equation again, right? X dx plus y dy equal to 0. I just covered that up here, right? As you can see, the solutions to it are circles. And these dashes are actually, representative of a line dy dx with the slope, the slope given by the differential equation. But let's try to figure out what that is. So if I have, because that's not immediately obvious, but if I have x dx plus y dy equals to 0, the slope would be what? Dy dx equal to what? So I put x dx on the other side, and yeah, I get, is it minus x over y? Is that it? I think that's it, right? So that's the differential equation, right? Which vector field?
Is that the one we just did?
That was negative y.
It's x over negative y.
Did I do the math wrong? That's possible. Y dy equal to minus x dx. So dy over dx equals to minus x over y. No, that's it. Yeah. It's the same. It's just the minus is in the denominator rather than the numerator, right? Same thing. There we go. Whew. Okay, so what vector field are these the integral curves for? Many, many different ones, but one obvious one is if you go back, if you think of this as like, Q over P, I mean, we just did it, so you know that it's the integral curve for the vector field, goodness gracious, minus, oh, my brain's not working, minus y comma x, right? Great. So that's one. Here's another one. Here we've got dy dx equal to x plus y minus 6 squared. So let's talk about the geometry of what's going on here. Your solutions would have slope 0 where? Yeah, but can you see from the equation? Where would we have slope 0? We need what? X plus y minus 6 equal to 0, right? So that's y equals to
3.
6 minus x. Well, I mean, it's a whole line. There's a whole line along which, if any solution gets to that line, along that line, it has to cross it like a level, like a horizontal path. See, so if y equals 6 minus x, I think it's in here somewhere. Rats, I don't have any numbers, but let's see here. So yeah, that's kind of all the point of that example was. Now it turns out that if you go back in my notes, I solved that previously. I think we might have solved that in here as well. It was maybe the first substitution problem we did, maybe. But you can solve it by substitution, I believe. And its solutions are 6 plus tangent of x plus c. That, as it happens for different values of c, it looks like this. See the tangents blow up, like so. All right. Here's another one. We have x plus y plus 2 times dx times plus x minus y dy equals 0. And so if I rewrite it in y prime form, I've got y prime equal to x plus y minus 6 squared. That's 0 where? Like y prime equal to 0 where? If you think about it, we want x plus y minus 6 squared equal to 0. So we if we have, I guess it's the same thing again, isn't it? Y equals 6 minus x is going to be this dy dx is equal to 0 along that. I'm not saying that y equals 6 minus x is actually a solution. It may or may not be. I don't know. But if your solutions approach that, they should have like slope 0 on that point. Those points. So let's see if we can see it. So 6 minus x. You might be able to kind of, if you look in here, somewhere in here, there's a place where you've got like horizontal tangents. Maybe here. That's, if we could see the numbers, that would be 6 minus x. That's where you're getting slope 0 in the slope field. So. This one is more interesting. This is the isocline field for dy dx is, well, that. All right. And if you rewrite that, this involves polar coordinates. And it's a funny thing. Any solution inside the unit circle, I forget, it either spirals out to the unit circle or into the origin. I forget which. I guess it doesn't matter because this is just x, so there's no sense of direction. But so like the solutions here will continue all the way out to like the unit circle, and then outside the unit circle, they all get sucked into the unit circle like that. Yeah, I think if you look at the denominator there, I believe it's 0 on the unit circle. So the differential equation it's not quite defined on the unit circle, and that's why there's really interesting behavior there in the limiting sense. So. Now you might wonder how I made these pictures. I think what I did was, there's a way to do this with the p-plane tool in MATLAB. So let me show you that. So this thing, here's a website for it, but it's actually in MATLAB, which you guys know how to use, p-plane. I mean, you may not know how to use p-plane yet, but let me show you how it works. So for instance, if I want to go back to my earlier example, which dy dt equals to minus y, and dx dt equal to, what was it? Dx dt equals minus y, was it? Yeah, dx dt equals minus y, and dy dt equals to x, right? I could do that directly. Graph phase plane. There you go. This is actually so this is not an isocline spot. This is a direction field, right? So the arrows point in the direction which go. And if you click on here, it will pick the solutions that go through that point, which is pretty cool because we can do this for differential equations that we can't actually solve. We can still look at what the solutions look like because these are generated numerically. Now, so another way to get at this is to what you can do is you just do like, what was my differential equation? dy dx is minus x over y, right? So, sorry, my brain's not working entirely today, so I think I do. I mean, I can show you, I just can't explain it. So x divided by y goes here, my bad, in the y. Minus x over, I'll get it eventually. Minus x over y goes there, I think, and up here I just put 1. And so what that does is, well, first of all, it creates some funny stuff happens, right? Y equals to 0, we get into some trouble there. But this way I can plot the direction field. So if you just ignore the arrows, what I'm trying to say is you can use this thing, just ignore the arrows, and it basically gives you the isocline plot. So if I could remember this fancy schmancy formula for the one we were just looking at, I wonder if I put t here instead, if it would do better. I don't know. Oh, I don't know that though, it's y. Of course down here, so it's you know, it's having trouble at 0, as it should, because it's not quite defined there. Let's see if I can think of another one. What if we had like x squared divided by y? Let me just do x squared times y squared. That might be interesting. So this is what the direction, well, essentially the isocline field looks like for dy dx equals to x squared to y squared. So all I do basically is put dx dt equal to 1. What I'm trying to say is I'm looking at it as, it's a kind of dumb system of differential equations. To use this tool, if I just put dx dt equals to 1, and then I put dy dt equal to like f of x comma y, then this, you know, in p-plane plots direction field for dy dx equals to f of x comma y. So, I mean, the thing is, this particular tool is set up for a system of differential equations, right? But we're not there yet. So, but we can still use it if we just do this little trick, which is to put dx dt equal to 1, and then we just put dy d equal to whatever we're interested in looking at. So now we could solve this one, right? But I will not chase that rabbit. But everyone here should be able to easily solve dy dx equal to x squared y squared, right? Separate, integrate, you'll have a solution, right? What did that solution look like? Looks like these. Right. Looks like those. So I wanted to show that to you. Let me get back to my notes here. So we, you know, all this time we've had in here solving various problems, and I've showed you all kinds of, you know, very creative solutions and so forth. But we haven't yet addressed the fundamental question, which is, when can you solve the differential equation? Right? If I just write dy dx equals to f of xy, does it work? Like, can I be sure that I'm going to be able to solve it? And if I can solve it, is there going to be a unique solution which goes through a given point, right? So the theorems that I'm projecting right here give answers to those questions. And the answers are surprisingly simple. For example, theorem 2.65 here, we learned that if we have a continuous function on a rectangle, then at least one solution exists for dy dx equals to f of xy at each point in the rectangle. Moreover, these solutions exist to the edge of the rectangle. They can be continued to the edge of the rectangle. This is very cool. So like if you have dy dx equal to, say, x squared y squared, right? Where is that continuous? Where is x squared y squared continuous? Like let me put it a different way. Is there any place in the plane where x squared, y squared misbehaves? No. So that means if you pick any rectangle in the plane, right? If you pick a solution to this differential equation, it will exist inside that rectangle all the way to the edge. And if you pick any rectangle in the thing we were just looking at, right? In that, now I put my website. If you look at these, make a rectangle, wherever you want. You'll notice every solution inside that rectangle just continue. It doesn't blow up or anything, stop or cease to exist, or in fact, more than that, it's unique, right? I believe that, well, maybe some funny stuff going on over here, right? See that? I'm not sure about, I'm not so sure if we kept looking over here, maybe we might have trouble, maybe. Let's go back to my notes. So the second theorem that I wanted to share with you guys is uniqueness of solution. So suppose f is continuous on the rectangle, all right, and its partial derivative with respect to y at that point is non-zero, all right? If that's the case, then there exists a unique solution through that point. All right. Now the proofs of these theorems are well beyond the course. I think I more or less proved both of these theorems in a course I taught in advanced analysis last semester. So if you're really interested in that, you can look at those. But it's not easy to prove. It's kind of a pain. But it's instructive to look at an example. This one, for example, dy dx this is a really nice example because it illustrates the fact that differential equations have some really weird behavior in a certain sense. As I look at the differential equation dy dx equals to y squared, right? It's a pretty nice differential equation, right? Yet the case is, if you start the solution, if you look at a solution to this differential equation, you can't just, you're not going to be able to continue the solution. Let me show you. So the solution to it ends up being y is equal to minus 1 over x plus c. So there's a vertical asymptote in the solution. But if you look at the differential equation, it doesn't look like it has any kind of vertical asymptote, but it's there. Because this differential equation grows so fast that it can't keep growing at that rate forever without basically creating a vertical asymptote. I think this is known as super exponential growth, if I remember right. But anyway, this differential equation, the f, if you will, of xy is y squared. And what's the partial derivative of y squared? Well, it's 2y, right? So right there, so if we pick a point where that's 0, which would happen where? Y equals to 0. At y equals to 0, we can't be sure that we're going to have a unique solution. And in fact, if you think about this differential equation, you have y equals to 0 as a solution. That's one solution, right? But you also have solutions of this form. But I don't know if those actually cross 0. Here's another one. dy dx equals to 2 squared of y. If we take the partial derivative, well, first of all, the solution to this, we can separate, we can integrate, we get this. Our solutions are actually parabolas that they bounce off the x-axis at minus c, right? This is a parabola that opens up at minus c. But on the flip side, this also has what equation? What solution? How about y equals to 0? Is that a solution to this? It is, right? Is the derivative of 0, 0? Yep. Square root of 0? 0? Yep. So 0 solution solves this. Yet this also solves that, and those do intersect at the points on the x-axis where y equals to 0. That illustrates this theorem. I don't think there's actually a non-uniqueness in the previous example, except in a limiting sense, which isn't what I mean by it. But here's a picture. So the tool that I had, you put red dots outside the domain of the differential equation, which is pretty cool. I think P-plane does this. So this says, hey, your differential equation is not defined here. It's defined up here, right? So you got the 0 solution, and then you've got, these parabolic solutions, but you're only seeing half of them, right? at the moment. But yeah. Let's see here. Oh, end of the road. So any questions? I think at this point I will start into the applications. So we'll go back and we will dive headfirst into the applications problems. I think I will talk about this example before I put this away because this one I can't, I mean, you really need to look at the projection for this one for sure. This is example 2.55. The question is to find a family of curves that's increasing whenever y is less than minus 2 or y is greater than 2, and it's decreasing whenever minus 2 is less than y is less than 2. So I'm asking you to create a family of curves which behaves this way. So one way we can do that is we can build a differential equation which has this behavior. So what does it take for a function to be increasing? It needs a derivative which is positive, right? What does it take for a function to be decreasing? You need a negative derivative. Which function behaves as I want here so that it's, it's negative over here, it's positive for less than minus 2, it's positive for y greater than 2, and it's negative in between. So that makes me think of a parabola. That's how a parabola behaves, right? So now this is a parabola in y, so to speak. But you see if I have this formula right here, y plus 2 times y minus 2, it's going to be negative between these two, and it's going to be positive over there and over there. You can try it out. If you plug in 0, you get minus 4. Plug in 3, you get 5 times 1. Plug in minus 3, minus 5 times minus 1. So it's positive on the edges, and it's negative in the middle, just like we want. All right? And if I solve dy dx equal to that, the solutions to that differential equations will behave as I'm describing. They'll be increasing where we want and decreasing where we want. So that's what I do. I have to solve this equation. Ugh. Dy dx equals to y plus 2 times y minus 2. So I separated, and then I integrate. You'll remember partial fractions. There it is. So we partial fractions that thing. Then we can integrate. And then the natural log of a difference is the natural log of a quotient. Then I did some algebra here. Why did I do that? Interesting. Oh, I was making it a proper denominator. So I was, this is like an improper fraction. I was factoring out that. That's going to give me 1 plus that. Fine. So that's nicer for the steps that follow. I get the natural log of the absolute value of 1 minus this equal to that. Then I exponentiate both sides. Right, exponentiate both sides, which gets me to this, which gets me then to plus or minus e to the c, e to the 4x, which we can just write as a big constant k times e to the 4x equal to this, which then if I isolate the 1 over y plus 2, I get this, dividing by 4 that, and then subtracting 1 to the other side. I think I multiply by minus 1 after that. Anyway, so I get this, and then reciprocate and subtract 2, and voila, there's your solutions. This family of functions behaves in such a way that it's increasing and decreasing just like we said. And I can visualize that with the p-plane. Watch. So here's the differential equation. Y prime is y squared minus 4. Y squared minus 4 is y plus 2 times y minus 2, okay? Right? And as you can see, we're increasing down here and up here, and we're decreasing right there, just like we wanted. And also, you notice that because the differential equation is only a function of y, there's a symmetry in the sense that no matter where you are on x, it's the same as you go from one side to the other, right? That's not actually true on x. It's very much based on your likes and preferences and timeline. But in this x, it's the same, like that. So, I'm sorry, you guys you're like on Instagram. Is that what's going on here? You're on TikTok, but now you're sad. That was a Twitter/X joke followed by an Instagram